Well, hello all and welcome to week number 5. This week we're going to be preparing for the statistics exam. So we have a couple of final chapters to read in the stats book. So chapter 10 is going to cover analysis of variance. We're going to talk a little about that today, usually called an ANOVA. We're going to talk about chi-square, which is covered in chapter 11. And then chapter 12 is going to talk about applying these statistical methods. Okay, so let's refresh on the types of variables. So we know that there are 3 types of variables, or at least we're combining them into 3 different types. The first one is a nominal variable. These are variables that have categories. That's it. There's no ranking to them. There's no anything else to them. So things like gender or race, ethnicity, religion, eye color, hair color, things that just have categories, those are known as nominal variables. From a statistics vantage point, it is critical that you know the type of variable that you're working with, because then you're going to know what statistics you can run on those variables. There are some variables where we can run certain statistics and other variables we run different statistics on. So being able not only to create your own variables, but to identify immediately what types of variables are out there and then what statistics you can run on them. Next type of variable, as you know, is an ordinal variable. These are variables that have categories very similar to the nominal variables, but there is a ranked order to them. So this would be freshman, sophomore, junior, senior. Freshmen are lower than sophomore, sophomore are lower than juniors, etc. This could be low, medium, high. Anything that has a ranked order, but there's still categories, that would be an ordinal variable. The last type we're going to combine into one, calling them an interval ratio variable. And these technically are categories in ranked order with equal intervals. Easiest way to think about this is just a number. So if I'm going to get your age and I ask you which age category do you fall in, are you 20 to 30, 31 to 40, 41 to 50 and on up, and I ask which is your category, that's an ordinal variable. But if I ask how old are you and you give me a number, then it's an interval ratio variable. So how are you going to define these variables? So if I was going to define a variable, let's say for a stat exam, I might give thought to what is the title I would give that variable. So let's say I'm going to call my variable gender, and I know that's an independent variable in my particular research. The type is a nominal because it's just categories, no ranked order to them. All right, because it is a nominal variable, the next thing I need to tell or explain is what are the categories. So I am going to have gender listed as male, and the way I'm going to define male is as identified on the birth certificate. And then I'm going to have another category called female, and it's going to be identified as what was on the birth certificate. Now I can change that. I can make it male, female, and other. I can make it 12 different categories. If you look at things like the Department of Health and Human Services, they have many, many categories here. It is up to you, the researcher, to define how you want to define or decide how you want to define your variables. You can also say it not as what it is on the birth certificate, maybe what it is on the driver's license, or you can ask them to self-identify. So it just depends how you want to define the variable, but each category has to be clearly identified. What I see happen is people will pick gender, and then rather than defining gender as what are the categories male and female, they'll say gender and then, well, do they smoke or do they not smoke? Well, that's a totally different variable. Be very linear in your thought process here. Get the title of the variable and then the categories, if it's nominal or ordinal, the categories for that variable, and each category has to have a specific definition. So if I have a title of a variable called program participation, in this case it would be an independent variable. The type of variable might be ordinal. Now I could have we are kings and queens of our own variables. We can define it any way we want. I might choose to define program participation as nominal. Yes or no, they participated or they didn't. Or I could do interval ratio. Program participation is defined as the number of hours they spent or the number of sessions they attended. Interval ratio. In this case, I'm going to define it as an ordinal variable. And so if it's ordinal, I know I have to have categories. And I'm going to say it's going to be low, medium, and high, or low, moderate, and high, I think I did. So low, I would define as attending 4 hours of training or less. Moderate is defined as attending more than 4 hours, but less than 12 hours. High is defined as attending more than 12 hours of training. You can do this any way you want, but it has to be specific. Keep everything in, and if you want to, if I was taking a stat exam, I might use this kind of a format if I was asked about some of the variables for my program evaluation. Remember, the stat exam is not a general stat exam. The answers are going to relate to your program evaluation that you are working on. So whatever program you're working on, you think about what variables might be used in your type of program evaluation. The other thing is, remember, you just finished a lit review, so there's probably variables and definitions and things in there. Utilize everything at your disposal right now. Okay, so one of the things I would think about if I was studying for a stat exam is what variables would work for my program evaluation and how might I define them. The next thing I might want to think about are measures of central tendency. So measures of central tendency include things like the mean or the arithmetic average. So when I'm dealing with, let's say I'm looking at the age of everybody in this class. Well, how would I calculate the mean age of everybody in this class? I would get everybody's age, add them up, and divide by the number of people in the class. That is my arithmetic average. That's showing me the center arithmetically of where age is in our class. The median is the number in the center of the collection. How would I get the median age of everybody in the class? I would take everybody's age, sort them from lowest to highest, and count into the center. Whatever number is in the center of the collection would be my median. If there are two numbers in the center of the collection, an even number, then I would take those two numbers, add them up, divide by 2, and that would give me the median. If I wanted to get the mode, which is the most frequently recurring number, I would put everybody's age in, from lowest to highest, find where there are more than one of a certain age, and that would be the mode, the most frequently recurring number. So I want you to start thinking about mean, median, and mode, and these measures of central tendency, and how they might play in with your type of research. Now I want you to start thinking, and I'm not going to give you the answers to this, but if you need me in a Zoom session this week, we can maybe discuss it more. But if you wanted to buy a home in a city, let's say Rancho Cucamonga or Riverside or wherever, would you rather know the mean housing price, the average housing price, or the mode, or the median? Now I want you to really think about this. If you have the average housing price, now let's say I've got, in Riverside, let's say houses are going for $200,000. So I've got a 200,000, 200,000, 200,000, and then that one house up on the hill is going for 2.1 million. Well, think about that. Then what would the average price be? Well, I'm going to add that 2.1 million and a bunch of these 200,000. So my average price is going to be, I don't know, hundreds of thousands of dollars higher and lower than the real prices. So it may not give you the information you're looking for, or maybe it would, depending on what you're looking for. The mean is going to be very sensitive to what we call outliers. So that 2.1 million is going to really pull that average up quite high into an area that maybe no houses are actually selling for. The mode, the most frequently recurring number, if you've got a 2.1 million and then a bunch of these 200,000, well, maybe that would give me some indication. The median is going to show you what number is in the center of that collection. Now, you may want a combination of all of these. Maybe all of these together would give you a better overall picture of it. But I really want you to think about which of these would you personally find most useful if you could only have one of them, and why would you want that one? Now I've got another think question for you, and this is really critical to understanding what's about to come with more statistics. Can you get a mean, an arithmetic average, can you get a mean on a nominal variable? Pause there for a minute. And if you're watching this on YouTube or whatever, go ahead and pause, and I want you to think about that. Now that you're back, I want you to think about, can you get a mean on an ordinal variable? Pause and think about that for just a second. And can you get a mean on an interval ratio variable? This isn't to quiz you. This is for you to really understand what these numbers mean, what these types of variables mean, and how they all get related. So hopefully you took 10 seconds or whatever and actually thought about this. The answer is you cannot get a mean on a nominal variable, because the way you get a mean is you add up the numbers, divide by the number of cases. Well, if I've got red, green, and blue are my nominal variables, I can't do anything with that. I can certainly assign them a number, saying red is 1 and green is 2 and yellow is 3, but they don't mean anything. They're not meaningful numbers. So the answer is no, I cannot get a mean on a nominal variable. If that answer does not make sense to you, don't just take it as to memorize it. I need you to really understand this. If it doesn't make sense, please ask your study group. If your study group wants to meet with me, then we can discuss it further. The answer is also you cannot get a mean on an ordinal variable. You cannot get a mean on low, medium, and high. Now, there are many times that we will try to get a mean on, let's say I say on a scale of 1 to 5, how satisfied were you? Were you 1 not satisfied or 5 very satisfied? And we tend to run means on this, but they're technically not meaningful. So although we do get means on ordinal variables, technically we cannot do that. The only one that we can get a mean on is an interval ratio variable. Anchoring to this particular slide is really critical for the rest of what's about to come. So please make this make sense to you. And if you disagree with it, good. Work it through. Talk to somebody in class. But you've got to work through this particular slide for everything else to begin to make sense. Okay, let's talk about types of distribution. If I have a curve, these are called curves. If I have a curve that looks like this is called a normal curve. Some people will refer to it as a bell curve, other things, but the technical name is a normal curve. On a normal curve, there's an interesting thing that occurs, that right here, dead center, is the mean. So in a normal curve, the mean, the arithmetic average is, let's say there's a number line at the bottom, it's going to be dead center. The median, the number in the center of the collection, is also at the exact same place, and the mode, which is the most frequently recurring number, is going to be at the pinnacle there, because you think, if you're out at either one of the right or left side, very few are there. as you move in towards the center of the curve more and more, and then the mode, the most frequently recurring number, happens at the peak there. So on a normal curve, your mean, median, and mode all line up. Okay, so that is a normal curve. Let's say we take everybody's age in this class and we plot it on a curve, and it looks like this. So we have one very young person, one who's a little on the older side, relatively speaking, and then we've got most everybody in the center of that curve. So let's say, just for argument, this is what our class looks like. Then what's this curve called? Well, we can see that if I cover up this tail right there, and let's argue that that's going to be a normal curve. All right, so if this would be a normal curve, that's maybe what our class is, what had to happen for this tail to occur? Well, if this was our class, we were a normal curve, in order for that tail to get pulled down low like that, that means somebody very young, a 5-year-old, a 7-year-old, had to join our class. So then you take that normal curve up on top and you have to pull that left tail to the negative side, to the lower side. So we refer to this curve as a negatively skewed curve because that very young person skewed the curve to the lower side. Conversely, if I have this curve, it's called a positively skewed curve. Same thing, if this was a normal curve like on top, which was our class, then who would have to come in to get that tail pulled out there? It would be a very old, not even a very old person, an older person would pull that tail to the positive side. So the normal curve is on top, the negatively skewed curve is in the middle, and the positively skewed curve is on the bottom. Then what kind of curve is this? Well, what I'm seeing are two peaks in there. I have one peak on the left side, one peak on the right side, and we usually refer to those peaks as the mode, the most frequently recurring number. So in this one, I have two modes, or a bimodal curve. So two modes, bimodal. So let's look again, let's take from the top. If I have just an average kind of class, some younger, some older, a lot of people in the middle, that's the top curve. The one below it, the negatively skewed curve, I could have still kind of the same thing, some older, some younger, most people in the middle, but one outlier, very young, would create that negatively skewed curve. The next one, the positively skewed curve, again, I have some older, some younger, but one very much older person pulls that tail to the right, meaning a positively skewed curve. In this bimodal curve, it's saying I have a grouping on the lower side and then a grouping on the higher side. So two modes. So if I'm thinking about something like rush hour traffic, that would probably be some sort of a bimodal curve, because at 1 in the morning, 2 in the morning, not much traffic. Now going up that curve, it's now 3 a.m., 4 a.m., 5, I don't know, when's rush hour traffic? 6 o'clock, 5 o'clock, I don't know, 7. Then we're peaking up around 7 or 8. And then maybe it kind of, I don't think in LA it ever goes back down, but let's just say it goes back down, and then starts coming up about 4, 5, 6, 7 o'clock, and then starts going down. So maybe rush hour traffic would be a bimodal curve. Now, if you're looking at your research, what kinds of variables would you use for for any curve? What kinds of variables would you use for a curve? Well, remember, the mean, median, and mode are all aligned on that normal curve. Can I get a mean on a nominal variable? The answer you should be yelling back at me is no. Can I get a mean on an ordinal variable? No. Can I get a mean on an interval ratio variable? Yes. So when I'm looking at things that create curves, I can only look to an interval ratio variable. Now let's talk about the stat exam. If you're asked a question like this, and you currently do not have any interval ratio variables, create one for the purpose of the exam. Something that would make sense for your research. So you should have different types of variables that you can use as examples. Okay, so now if I were studying for a stat exam, I might think about one of my interval ratio variables, and if it was going to result in a curve, what might that curve look like? You don't have the data, so you're only projecting, you're guessing what it might be. And this is all hypothetical. So let's look at the age of gang members in Los Angeles. Now, there's no right or wrong answer, but there's a right or wrong logic behind it. So if you were to tell me, well, you know what, there's a few 10-year-old gang members and a few 30-year-old gang members, but the majority of them are 22. I'm making all this up. And I think it would be a normal curve. You know, there are a couple young, couple older ones, and everybody in the middle. Well, then that would be a rationale for a normal curve. Or if I go to the next curve, if we say, well, the gang members are generally 18 to 30, but I do have a few, God forbid, 9-year-olds that got jumped into a gang. So if the bulk of them are sitting between, what did I say, 18 and 30 or something like that, 17 and 30, but those very young gang members are going to pull it, that's going to result in a negatively skewed curve. Let's go to the next one. I've got gang members in my city, and they are generally between 14 and 30 years old. However, I've got a few of those old gangsters, those OGs that are in their late 50s, early 60s, that are pulling that tail to the right, giving me a positively skewed curve. Let's go to the bottom one. In my city in LA, I've got young people in the gangs kind of going up, kind of peaking around 16, 17, 18. Then when they get in their 20s, they're now arrested and they're in jail. So I really don't have much in the way of the 25-year-old gang members because they've all gotten, put away in jail. But then they're coming back out. So then I have this next hump of gang members that are in their late 20s into their late 30s, but I just don't have anybody in the middle, so I have a bimodal curve. You just have to be able to tell the story that makes sense for your variable, and you've picked the correct curve for it to match. I want to caution you, if you are using either the negatively skewed or the positively skewed curve, remember what causes the skew is the outlier. It is not where the majority of people are. If you have the majority of people around 17 years old, then it's probably a normal curve. But if you have the majority of people around 17 years old and you have an outlier, very young or very old, that would create your skew. Remember, this stat test is not about calculations, it's about language. It's about your ability to convey a message verbally about the statistics that you're seeing. Okay, so far we've been looking at measures of central tendency. How central are the data? Mean, median, and mode. The next area is called a measure of dispersion. How wide are the data? How far on each end are the data? So when we do that, we're trying to determine how homogeneous or heterogeneous my variable is. So how alike or how dissimilar the data are. One of the measures of dispersion is called range, and that's the difference between the lowest and the highest numbers in a data set. So the way that I calculate range is I take the lowest number, I subtract it from the highest number, and I have a range. So if we gave an example, what is the price range for a new car for you? And you might say, well, I'm going shopping this weekend, and I'm looking at ones between kind of the $30,000 to $32,000 range. Okay, so that means my range is $2,000. If somebody else said, you know what, I'm not real sure, I'm kind of looking in the $15,000 to $20,000 range. Well, they've got a bigger range than I do, lower amount maybe, but a bigger range. They have a $5,000 range to play with, whereas I've only got a $2,000 range to play with. So we're looking at the range on this. A similar but quite different calculation is called standard deviation. And standard deviation is the typical deviation from the mean. Now, once again, we're dealing with mean. Can I get a mean on a nominal variable? No. Can I get a mean on an ordinal variable? No. So standard deviation can only be used for interval ratio variables. Okay, the same thing with our mean, same thing with standard deviation, same thing with range. All of these can only be operated on an interval ratio variables. So for some of you, I've given you feedback in the past. If you have the option of collecting data as an ordinal variable, like age range, or you could collect it as the exact age of somebody, always go for the highest level. Get the exact range, because if I'm reporting it, I can always roll it into categories on the back end. But if I only have the categories as an ordinal variable, I can't move it forward. Okay, so standard deviation is going to show me the deviation from the mean. Okay, so all I need you to know are these numbers. That one standard deviation from the mean is 68% of the data set. So remember, we're looking like right here in this curve would be the mean, would be dead center, would be average. And then one standard deviation plus or minus would account for 68% of all the data in that data set. Now let's look at this. Mean, meaning average. So if this was the average test score and you were a +1 standard deviation from that mean, meaning you did a little bit better than the average person on that test. A -1 standard deviation, you did a little, not too bad, but a little worse than everybody else on that exam. I need you to also memorize that 2 standard deviations will account for 95% of the data in the data set. So in that case, 2 standard deviations from the mean would mean, we've done worse than the average on a -2, or better than the average on the +2. The last one is 3 standard deviations will account for 99% of all of the information in that data set. So -3, I'm not doing well if I was taking a test. +3 standard deviations, I'm up in that kind of 0.5% of people doing very well. So again, the standard deviation from the mean or the average, that's what the standard deviation is going to tell us. All you have to memorize is that 68% will fall within ±1 standard deviation from the mean. 95% will fall within ±2 standard deviations from the mean, and 99% of the data will fall within 3 standard deviations from the mean. These are just calculations, so all I want you to do for our purposes is, do you remember there was a commercial, it was like this Staples, there was this big easy button, and people would just hit the easy button, and I don't know, it was easy to shop at Staples or something. Well, just picture that big easy button, and you're going to hit, give me the answer in standard deviation, and then it's going to give it to you. Don't worry about how to calculate this. All I want you to know is that in a normal curve, 1 standard deviation accounts for 68% of all the data, 2 standard deviations equals 95%, 3 standard deviations equals 99% of all the data in that data set. So let's look at, I'm just making an imaginary thing for our class. Let's say we've taken everybody's age in the class, we've added it up, divided by the number of cases, and we know that the average age of everybody in our class is 33 years old. I have no idea. This is probably not accurate at all, but let's go with that. And then I know that one standard deviation equals 2. So if the mean is in 33 years and one standard deviation equals 2 years, then we know how many years it is. So now what do we know? If we have this information, what do we know? Well, we know that 68% of everybody will fall within plus or minus 1 standard deviation from the mean. So that means that 68% of everybody in class will fall between the ages of 31 to 35. 2 years, on the positive side of the average, 2 years on the negative side of the average. We also know that 95% will fall within plus or minus 2 standard deviations from the mean, meaning 29 to 37 years old. And we know that 99% of everybody in class is going to fall within the ages of 27 to 39 years old. Okay, hopefully this is making sense. If not, please work with your study groups on this, and please invite me in if you need me. Okay, so now we know that the 1 standard deviation equaled 2 years for our class, but now let's look at a 7th grade class. And let's say the average age of the students in that 7th grade class is 12 years old. But now, rather than 1 standard deviation being 2 years, like it was for our class, 1 standard deviation here might just be 0.25, a quarter of a year, or 3 months. So now what do we know? We know that 65% of all of those students are going to fall within 11 years, 9 months, and 12 years, 3 months, meaning 3 months on either side of that average age. 95% will fall within 11 and a half years and 12 and a half years old, and 99% of those students will fall within 11 years, 3 months, 12 years, 9 months. Couple of things here. Which group is more alike? Our class with regards to age, or the 7th grade class? Well, the 7th grade class has more similar ages than our class. The standard deviation is lower in theirs, higher in ours. So the higher the range, or the higher the standard deviation, the more dissimilar that data set is. And the lower the standard deviation, lower the range, the more similar or homogeneous that data set is. Here's an exercise I'd like you to consider doing, because I want you to be able to visually see what these numbers, the story that's being told from these numbers. So here, if I have a weapon, and the weapon it can drop flowers, it can drop teddy bears, it could drop whatever, but we're just going to call it a weapon for our sake. And let's say this weapon is getting dropped out of a plane. So the first weapon I have is called Killer Lynx. And what this is saying is that on average, mean, that when I drop this, let's say from a plane, it's going to hit on average 25.25 feet away from the target, with a standard deviation of 20.99. Mountain lion claw is hitting 15.5 feet away from the target. Remember, I'm dropping this, with a standard deviation of 40.42. And gray bear punch is hitting 16.2 feet away from the target with a standard deviation of 13.2. What I would like to challenge you to do is draw what you're seeing. These numbers should be giving you a visual image of what's happening, and I'd like to see you draw this. We can probably logically figure this out just by looking at it, but it's different to just work off of numbers, and it's different to be able to actually see this. So if the same thing, similar to this, if I'm talking about, I have a new person hired in, I've hired Bob in to fill tire pressure, fill tires with air in my auto repair shop or whatever. And I say, how's Bob doing? Oh, on average, let's say all the tires, I'm making this up, have to be 32, we're just going to make it easy, 35 pounds per square inch, or yeah, PSI. So how is Bob doing? Well, yes, on average, he's filling all tires to 35 PSI. Now I might want to say, but what's the standard deviation? Well, one standard deviation equals 0.25, meaning a quarter of a pound. You should be able to see those tires rolling off that lot. Does it look okay if one standard deviation equals 0.25? If I say, how's Bob doing? He's doing well, filling tires to 35 PSI. I ask, what's the standard deviation? And you tell me 5. One standard deviation equals 5 pounds per square inch. What do those tires look like? So I want you to be able to see, not just look at the numbers and figure out what the numbers are doing, but what does that look like? So I'd like you to try this exercise. And again, if you want to talk to me on the phone, or I could meet with your group, this is a good exercise to work through. Okay, now we're on to a z-score. Up until here, again, if I was studying for a stat exam, I would think about what types of variables would work for my program evaluation. What would they be? How would I define them? I would think about when, for my program evaluation, might I use a mean, median, and mode, and what would that tell me? If I was studying for a stat exam, I would think about which of my variables could result in a curve, and what would be the logic behind the shape I think it would end up being. And I would think about standard deviation and range. When might that impact my program? The next thing I want to talk about is a z-score. Z-scores, again, can only be used for interval ratio variables. The way that a z-score works is you pick any number in the data set, and then you're going to hit that big easy button that says z-score, and it's going to tell you how many standard deviation that single score is from the mean. So if I say, if I'm in the office of a K-12 school, and Johnny's mom comes into the office and she says, my Johnny's a genius. Look at this, look at his test score. And you hit a z-score for his test score to see where he falls in relation to the mean. If Johnny's mom comes in, my Johnny's a genius, you hit a z-score and the z-score comes back -2, what do we know about Johnny? Well, we know that Johnny, that test that her son took, is -2 standard deviation from the mean. So Johnny isn't even average. He's 2 standard deviation away on the low side, negative side, from that mean. So now we know a little about Johnny. All right, new scenario. Johnny's mom comes into the office. My Johnny's a genius. Look at his test score. We take his score, hit a z-score on it, and the number comes back 3.1. What do we know about Johnny? Well, we know Johnny might be a genius. He's doing pretty good. He's better than 99% of everybody out there. So the way that we utilize a z-score is we pick one number from the data set, hit a z-score button for that number, and the answer comes back in standard deviation. If I were studying for a stat exam, I might think about when might I use a z-score and what might that information tell me. Similar but different to a z-score is a z-test or t-test. The difference here is that you're using a sample mean versus the population mean. So on a z-score, it's a single score against the mean. Here, it's the mean against the mean. So if I'm trying to do a z-test or a t-test, a z-test I would use if I had a sample over 100, t-test I would use for under 100. I'm just going to use the word t-test for now, meaning under 100, only to differentiate it a little easier from the z-score. So z-score, score against mean. T-test, mean against mean. So what does that mean? What does that mean? So I have an after-school program, and I have my kids studying for the SAT test. And I want to take the average mean average test score of the kids in my program and compare it to the average test score of the high school or the school, whatever. So I take the average of my kids compared to the average of the school, I hit a t-test button, results in standard deviation. So again, like a z-score, if I say, okay, here's the average test score of the kids in my after-school program compared to the average test score of the high school, and if the answer comes back 0, what do we mean? We mean that we are right, smack dab, 0 standard deviations from the mean, meaning we are right on the mean. We are average with everybody else. Well, does that mean that my after school program is good or not? Well, it really depends. So I would need to determine, so let's say that it comes back 0, meaning the average of my kids no better than the average of anybody of the high school. But if I was doing a program evaluation, I would be sure to get a pre-test on that. I would be sure to get that, what did they start as, and then what are they now? Because even if they are average now, if they started well below average, then my program may be really good. Even though they're no better than the rest of the high school, at least I was able to get them up to C level, so to speak. So the t-test is going to be average against average, and resulting in standard deviation. So if I were studying for a stat exam, I would think about when might I use a t-test or a z-test, and what would the results indicate. The next one, which is in one of your chapters this week, is an ANOVA, an analysis of variance. Very similar to the t-test and the z-test, where you had a mean against a mean. The difference with an ANOVA, and I'm just going to simplify it here, is that you can use more than 2 means, which means I take the average test score of the kids in my after-school program, I compare it to their kids in that after-school program, and compare both of those to the high school, the population. So it's mean against population mean. And then I can see which one did better, again, resulting in standard deviation. Okay, ANOVA, z-test, t-test, z-score, standard deviation, mean, median, mode, all of that, well, yeah, mean at least, can only be used for interval ratio variables. But what if I don't have interval ratio variables, or I have other things I need to determine, I need to get information on? One of the things that we can do is we can begin with a frequency distribution table that looks something like this. Now, again, pause the video here. How many variables are in this table? Okay, pause and think about that. How many variables are in this table? Okay, so now that you're back, how many variables are in this table? There, you should have been able to say 2. One is up here, meaning income, and the other one here, education. So I have 2 variables, income and education. I have my variable income is divided into 2 categories, low and high, which means this is an ordinal variable. My education is divided into 2 categories, low and high, meaning that education here is defined as ordinal as well. When you are setting up a frequency distribution table, you are using nominal and ordinal variables for a frequency distribution table. If you were going to be laying out a frequency distribution table for your research, then it should look something like this. You should also have not just the variable information, but a total column on the right side and a total row at the bottom. So this is how a frequency distribution table is set up. In order to do this, you're going to need nominal and or ordinal variables. Okay, so when I have these cross tabulation types of variables, What I may want to do is determine, is there a relationship between two variables? Is there a relationship between income and education? Is there a relationship? And in order to determine that, I'm going to run a test called a chi-square. It looks like chi, but it's chi-square. And I use a chi-square when I have two nominal or two ordinal variables, or one nominal, one ordinal variable. So the chi-square is going to show us if there is a relationship. Again, I'm going to simplify right now. Chi-square basically tells us if there's a relationship. But we need to turn to another calculation to find the strength of that relationship. So chi-square is going to tell us if there's a relationship between nominal and or ordinal variables. And then we have to turn to lambda or gamma to determine the strength of the relationship. So I would use a lambda if I have two nominal or a nominal and an ordinal variable, and I would use gamma if I have two ordinal variables. So once again, how you defined those variables and understanding nominal, ordinal, and interval ratio is critical to knowing how to run stats on the back end. After I run and I hit the lambda button or the gamma button, the answer is going to come out somewhere between 0 and 1. 0 meaning there is no relationship between those two variables, and 1 meaning there's a perfect relationship. For every time one occurs, the other one does or doesn't, depending. And then somewhere in between would be weak, moderate, or strong. So if I'm trying to determine, let's say I've got income and education, and I put in all my data, income and education, and they're both, let's say, we'll go ordinal. I have two ordinal variables. Income is ordinal, and income and education is ordinal. Now think about it. If you ran a chi-square on that, do you think there would be a relationship between income and education? Well, since you're all getting your education, I would hope you would say yes on that. So now we've got income and education, and we've got we know that we think there's going to be a relationship. Now we run a chi-square, and yes, lo and behold, there is a relationship. Now we're going to run a lambda or a gamma. Because I have two ordinal variables, I know I must run a gamma. How strong do you think that relationship would be between income and education? Do you think it would be perfect? Do you think it would be 1, meaning for every year of education you have, you make that much more money? Well, probably not, because people like Bill Gates and Steve Jobs, who ended up dropping out of college, are probably going to throw off, our numbers, along with Mark Wahlberg, the actor who dropped out of high school, but he's doing okay for himself. So we probably wouldn't get a perfect relationship, but we probably wouldn't have no relationship. So maybe it would be weak, maybe moderate, maybe strong. You would have your own rationale in there, and then we'd see what actually happened. But what I want you to be able to do for the stat exam is to project, what do I think it would be? What do I think the relationship? Would I run a lambda or a gamma? What variables would I use? Remember, in this area right now, we're talking about nominal and or ordinal variables. And then the last thing I want to touch, again, just conceptually on, is this concept of a bivariate regression. The big thing I want you to take away from a regression is it's working off of one independent and one dependent variable. A bivariate regression, bivariate, bi meaning two, variate meaning your variables, I have a two variable regression. And what I'm trying to determine is how much of a change does that independent variable cause to my dependent variable. So not just understanding nominal, ordinal, and interval ratio, but knowing which is dependent and independent is critical when you're running your stats. Like lambda and gamma, the range is going to be between 0 and 1. 0 says the independent variable does not explain anything about the change to that dependent variable. 1 says it explains everything. 0.4 says it is going to explain about 40%. So that's when I'm trying to measure how much of a change the independent variable makes to the dependent variable, I use a bivariate regression. If, however, I have multiple independent variables and I want to see which one of these causes the biggest change to my dependent variable, I can run a multiple regression. It's the same thing, it's just you do it all at once, and then you can see which of those independent variables is causing the biggest change to your dependent variable. Okay, so for the stat exam, it's going to begin on day 4, and it must be completed by day 7. So what does that mean? It'll get released on Thursday morning, and it will be due by Sunday night. The exam is open book, it's open notes, you can use the internet, you can use your lit review, look through the articles of your lit review and see, I'm sure you have some of these stats running through your lit review. You can phone a friend, use a lifeline, doesn't matter, just somehow get the right answer for your research. Everybody is going to be different because everybody's doing different research. Please use the Zoom room meetings to support each other. You can work together, so if next Saturday you want to meet in the Zoom room and ask questions and get help from each other on the exam, you are more than welcome to do that. I am off limits after Wednesday evening, so if you listen to this exam and you want to ask a few questions, set up a time, try to get your group together. And it's only because of timing I won't be able to meet with everybody individually, so please try to get your groups together, and I can answer questions from now until Wednesday evening, and then after that I'm off limits. So you can use any resource you have except me once the exam drops on Thursday. All right, if you have any questions, please let me know. This probably went by fairly quickly. You may have to listen to it a few times. And then also please find other videos that help explain maybe a chi-square or an ANOVA. Use whatever resources are out there that are going to help you. And remember, this is going to be there's no math in this, it's just very conceptual, and you're going to need to relate everything back to your program evaluation. So in the meantime, everybody have a wonderful week, and I'll talk to you soon.